So in this lecture, we're gonna look at the gaseous state of the matter. So since intermolecular forces in between the gas molecules are very weak, um, so the properties of gases and uh, some of the formulas for gases are very unique to that state of matter. So a couple of things about gases that we already know. So the intermolecular forces in between the gas molecules are very weak. So gases, they have indefinite shape, they have indefinite volume, and since they occupy um, lots of space, you would expect the density of gases to be very low. So since the density of gases are low, the unit that we use for the density of gases is grams per liter. Remember, for liquids, we use grams per milliliter, but for gases, the unit of density is grams per liter. Also, gas molecules, they have very high kinetic energies. Now, for gases, and in order to explain the properties of gases, we're gonna look at the kinetic molecular theory for gases. So let's see what the kinetic molecular theory is all about, and then we're gonna look at the behavior of gases at different conditions. So in the kinetic molecular theory, we assume that gases consist of very tiny particles, and we assume that the distance in between the gases is large compared to the size of gas molecules. Intermolecular forces are extremely weak, so gas molecules, they have no attraction for each other. And also, since gases have high kinetic energy, they move, and they move in a straight line. And they move in a straight line until they hit something. And once they hit a barrier, they're gonna change direction. Once they change direction, they're still gonna move in a straight line. They just change directions. Now, since gas molecules, they have high kinetic energy and they move, they're going to collide with other gas molecules and walls of the container. So in this theory, we're just going to assume that the collision of gas molecules are elastic, meaning that upon collision, energy is not lost. And also, one important thing is that the average kinetic energy of the gas particles is the same as the temperature of the gas. So the higher the kinetic energy, the higher the temperature of the gas. The lower the kinetic energy, the lower the temperature of the gas. And one important thing is that the average kinetic energy of gas molecules is directly proportional to the Kelvin temperature of the gas. So for gases, whenever it's about temperature, we use the Kelvin temperature of the gases. Now, in order to use this kinetic molecular theory and look at the behavior of the gases, a couple of things that I want to mention here and remind you. Since gas molecules move at a high speed and they collide with each other and the walls of the container, they're going to possess some pressure. So remember that pressure is force per area. Now, what affects the pressure are a couple of factors for gases. So number of gas molecules are important. So obviously, if you have more gas molecules, the number of collisions is going to be more. Temperature of the gas affects the pressure, because the higher the temperature, it means that the gas molecules are moving faster, so the collision is going to be higher, the pressure is going to go higher. And volume of the gas is also important in the pressure. So the smaller the volume, the higher the pressure, because the number of collisions is going to be higher. So pressure, number of gas molecules, temperature, and volume, these are all the factors that affect the behavior of gases. So we're gonna look at all these factors and see how behavior of gases changed if we make changes in any of these factors. Now, why are gases even important to us? remember that the air that we breathe is composed of gases. Air is a mixture of gases. So we are actually very interested in knowing the properties, chemistry of gases. Now, the air is composed of gases. So just imagine that you have all these gas molecules, nitrogen, oxygen, argon, carbon dioxide, neon, all these gases, they're constantly moving with high kinetic energy. And as they're moving around us, they're colliding. They're colliding with us, they're colliding with all the objects in the room, they're colliding with the walls too. So gases, even the air, has some pressure. That pressure we call the atmospheric pressure. And atmospheric pressure is very important when you do chemistry, because when you do chemistry in open air, when you set up reactions, just keep in mind that the air atmospheric pressure affects the reaction. So it changes the pressure in which the reaction is taking place. Now, atmospheric pressure was measured by a scientist, by an Italian scientist. So what this scientist did was that he got a capillary tube and filled up the capillary tube with mercury completely. And then he inverted this capillary tube into a bowl of mercury. So since you're inverting this tube, you would assume that all the mercury runs out. But this is not what the scientist observed. He actually observed that some of the mercury ran out, but the mercury stayed inside the capillary tube. So he suggested that the reason that all of this mercury doesn't run out of the tube into the bowl is because of the atmospheric pressure. So the gas molecules are hitting the surface of the mercury in the bowl, and the pressure that they're producing is pushing the mercury up in the capillary tube. So he got a ruler and he measured the height of the mercury in this capillary tube. So the unit of millimeters of mercury was discovered, and when he measured the height of the mercury at 1 atmosphere, it was 760 millimeters. So what you see on this table here are different units of pressure that we use for gases: atmosphere, torr, millimeters of mercury, centimeter of mercury, kilopascal, bar, and all these. So you see PSI, pounds per square inch. The ones that we use the most in chemistry or in this class are atmosphere, torr, and millimeters of mercury. So the conversion units are also given here. So each atmosphere is 760 torr, or each atmosphere is 760 millimeters of mercury. Torr and millimeters of mercury are, the ratio is 1:1. So they're the same thing. The scientist, the torr, the unit of torr is given, taken from the name of the scientist who discovered this. So make sure that you memorize the conversions in between the units of pressure. These three at least you need to know. So each atmosphere is 760 torr, or each atmosphere is 760 millimeters of mercury. And then also know that each 760 torr equals to 760 millimeters of mercury. So let's do a couple of practice problems to do unit conversions for the units of pressure. You want to convert 675 millimeters of mercury to atmosphere. So to convert from millimeters of mercury to atmosphere, you know that each atmosphere is 760 millimeters of mercury. So that would be 0.88 atmosphere. So let's do another one. You want to convert 675 millimeters of mercury to torr. So we know that each 760 millimeters of mercury is 760 torr. So let's do one more example. You want to convert 3 atmosphere to torr. So to convert, we have 3 atmosphere. Each atmosphere is 760 torr. And then the answer is 2280 torr. So let's look at another example. If you change the temperature of a sample of gas from 80 degrees Celsius to 25 degrees Celsius at constant volume, what happens to the pressure of the gas? Once the temperature decreases, it means that the kinetic energy of the gas molecules decreases too. So you would expect collisions with less intensity. So the pressure will also decrease. Now let's look at a couple of laws for gases. So in order to see the effect of pressure, temperature, number of moles of gas, and volumes, we're gonna keep the factors, all of them constant, and at each experiment we're gonna change 2 factors. So the first one that we want to look at is the Bohr's law, where we're keeping temperature and number of molecules of gas constant, and we look at the dependence of volume and pressure. So how this was done is that these scientists looked at the different pressures and measured the volume of the gas at different pressures. So after collecting data, Boyle basically graphed pressure versus volume, and he came up with this graph here. So as you see, based on the graph, pressure and volume do not have a linear relationship. But what we can also observe here is that as the volume increases, the pressure decreases. So Boyle came up with this law here, which is P1V1 equals to P2V2. Memorize this. And this is called Boyle's law. So P1V1 is your conditions first, P2V2 is pressure and volume after the change. So basically, if we make changes in the pressure, we should be able to find what happens to the volume. Or if you change the volume, you should be able to find what happens to the pressure based on Boyle's law. Now let's look at an example. A sample of argon gas occupies 500 milliliters at 920 torr. You want to calculate the pressure of the gas if the volume is increased to 937 milliliters at constant pressure. So V1 is given to us, which is 500 milliliters. P1 is 920 torr, and V2 is also given to us, which is 937 milliliter. So we're solving, so P1 V1 equals to P2 V2. We're solving for the P2. Now let's see how we can set this up. So P1 V1 equals to P2 V2, and we're solving for P2. To solve for P2, you can divide both sides by V2. Therefore, P2 equals to P1 V1 over V2. Now your P1 is 920 torr, V1 is 500 milliliters, and V2 is 937 milliliters. Now milliliters and milliliters cancel out, and you end up with the unit of torr. Which is 4 91. So when you set this up, you want to pay attention to the units. If I'm solving for pressure, after my setup, the unit that remains should be a unit of pressure. Also, on both sides of the equality, the units have to be the same. Let's do another example. A 6-liter sample of a gas at a pressure of 8 atmosphere is compressed to 4 liters at a constant temperature. What is the pressure of the gas? So let's see what's given to us. So a 6-liter sample of a gas, so meaning that V1 is 6 liters. P1 is 8 atmosphere. And we want to know if V2 is 4 liters, what is P2? So P1 V1 equals to P2 V2. So to isolate V2, we're gonna divide both sides by V2. Therefore, P2 equals to P1 V1 over V2. So P1 is 8 atmosphere. V1 is 6 liters. And V2 is 4 liters. So liters and liters cancel out. And you end up with 12 atmosphere. Now let's look at the dependence of volume and temperature. So keeping pressure and number of molecules of gas the same, we're gonna look at the change in volume when the temperature is changed. So if you look at the graph of volume versus temperature, you see that volume and temperature, the relationship is a linear relationship. So V1 over T1 equals to V2 over T2. This is the Charles law. Now keep in mind that in Charles law, or basically in gases, your temperature has to be in Kelvin. If it's not in Kelvin, the formulas are not gonna work out. Now let's look at an example here. A 2-liter helium balloon at 25 degrees Celsius is taken outside on a cold winter day at minus 15 degrees Celsius. What is the volume of the balloon if the pressure remains constant? So the only two factors that are changing are volume and temperature. So we're going to use Charles' law, V1 over T1 equals to V2 over T2. Now to isolate V2, we're going to do a cross multiply first. So V2 times T1 equals to T2 times V1. And in order to isolate V2, we're going to divide both sides by T1. Therefore, V2 equals to T2 times V1 over T1. Now, temperatures has to be in Kelvin. So T2 minus 15 plus 273 times V1, which is 2 liters, divided by T1, which is 25 plus 273 Kelvin. Now from here, Kelvin and Kelvin cancel out. We end up with liter. That tells us that the setup is correct. So the answer is 1.7. milliliter. So let's do another one. A sample of carbon dioxide has a volume of 200 milliliters at 20 degrees Celsius. What will be its volume at 40 degrees Celsius, assuming that the pressure remains constant? So V1 is given to us, which is 200 milliliters. T1 is 20 degrees Celsius plus 273 Kelvin. Now we want to know what the volume is if temperature is increased to 40 degrees Celsius. So since volume and temperature are the only two parameters, so we're going to look at V1 over T1 equals to V2 over T2. And in order to isolate V2, we're going to do a cross multiply. So V1 times T2 equals to V2 times T1. And then we're going to divide both sides by T1. So therefore V2 equals to V1 times T2 over T1. Now V1 is 200 milliliters. T2 is 313 Kelvin. And T1 is 293 K. Now K and K cancel out. That tells me that the setup is correct. So 200 times 313 divided by 293 is 214 milliliters. So let's look at the Gay-Lussac's law. So here we're keeping volume and the number of moles of gas constant, and we're looking at the change in pressure when you make changes in the temperature. So the relationship between pressure and temperature is a linear relationship. As the temperature increases, the pressure increases too. So P1 over T1 equals to P2 over T2. Now we can put all these three gas laws that we learned together to come up with the combined gas law, which is P1V1 over T1 equals to P2V2 over T2. So we're basically putting Boyle's law, Charles' law, and Gay-Lussac's law all together to come up with the combined gas law. So with the combined gas law, we actually have the ability to look at the change in pressure, volume, and temperature all at the same time. Now keep in mind that the temperature in this formula has to be in Kelvin. Pressure and volume has to have the same unit on both sides of the equation.